Hello, in this video we will be looking at how to use the stress and strain symmetry to reduce the number of elastic constants we need to consider for the relations of stress and strain. As you recall from the previous video, we showed for an anisotropic material to relate the 9 components of stress with the 9 components of the strain, we said we need 81 independent elastic constants. But now we will see that if we consider a stress symmetry, we can reduce this number of independent constants. From the moment equilibrium equations, one can show that sigma ij equals sigma ji. What it means is we have components like sigma 2 3 which is same as sigma 3 2. Similarly, sigma 3 1 is same as sigma 1 3 and sigma 1 2 is same as sigma 2 1. So, we are saying that sigma 2 3 is equal to sigma 3 2, sigma 3 1 equals sigma 1 3 and sigma 1 2 equals sigma 2 1. So, effectively we have reduced the 9 stress components to 6 stress components. Okay. So, which means instead of looking at all the 9 stress components, we can only focus on the top 6. So, we will only focus our attention in the top 6, because once we know these stresses, we can easily write what are the remaining 3 stresses, because these are the shear stresses have complementary terms which can be easily known. So, for us to find these only the first 6 stresses, instead of starting from these 9 by 9 elastic constants which is 81, we could focus only on the first 6 rows. So, with the first 6 rows we will have 6 times 9 which is 54. So, we only need to focus on these first 6 rows to get the complete description between the stress and strain relation. So, which means essentially we have reduced the number of elastic constants from 81 to 54 just by considering that the stress matrix is symmetry. Later we will use the similar argument for strain. So, again we can show that epsilon ij is equal to epsilon ji, meaning epsilon 1 2 equals epsilon 2 1 and epsilon 2 3 is strain 3 2, strain 3 1 is strain 1 3. So, essentially we are saying that epsilon 2 1 here is same as epsilon 3 2 and epsilon 3 1 is same as epsilon 1 3 and epsilon 1 2 is same as epsilon 2 1. So, essentially we need to only focus on the first 6 strain terms. Since we are focusing on the 6 strain terms, since we are only focusing on the 6 strain terms and we already have reduced the number of stresses to 6. So, instead of previously we said with the stress symmetry we reduced it to 6 by 9 which is 54 constants, but now we can limit only to the first 6 columns, because the last 3 columns which are relating the epsilon 3 2 1 3 and 2 1 can now be again written in terms of the other 3 shear components. So, we only need to focus on this 6 by 6 matrix which is 36 constants. So, essentially we started with 81 constants for an anisotropic material, then because of the stress symmetry we reduced it to 54 considering the stress symmetry. And now from 54 we have reduced it to 36. Here we have considered the strain symmetry. So, we just need these 36 independent constants to define the relation between the stress and strain in linear elastic anisotropic material. So, now we will see that instead of working with two subscript for the stresses sigma I and j, we can now use the contracted notation where instead of the double subscript we will replace it with a single subscript where I goes from 1 to 6. Since we said because of the stress symmetry we only need to focus on the 6 components of stresses. So, instead of 2 subscript we have came down to a single subscript where I goes from 1 to 6. Now, let us see how we write this. So, for the 6 components will be sigma 1, sigma 2, sigma 3, 4, 5 and 6. So, usually this sigma 1 is sigma 1, sigma 2 is sigma 2 and sigma 3 is sigma 3. So, as you can see the first 3 are the normal stress components. Then comes the shear stresses which are sigma 4 we will write it as sigma 2 3 and sigma 5 as sigma 3 1 and sigma 6 as sigma 1 2. But we already know from stress symmetry sigma 2 3 is also sigma 3 2 and sigma 1 3 is sigma 1 3 and sigma 1 2 is sigma 2 1. Similar to stresses we can do the same for the strains as well. So, instead of epsilon ij I can replace it with a single subscript epsilon I where again I goes from 1 to 6. So, we have these 6 components epsilon 1, epsilon 2, epsilon 3, 4, 5 and 6. So, the first 3 again are the normal strains which are epsilon 1 1, 2 2 and 3 3. And here we should be a little careful because for the shear strains in the contracted notations instead of writing the tensor strains we write the engineering strains which is gamma 2 3. So, we already know the engineering strain, how is it related to the tensor strain? It is twice the tensor strain, here it is 2 times epsilon 2 3. And for the others too we write it in terms of the engineering strains 3 1 and gamma 1 2. Again now writing in terms of the tensor strains this should be 2 times epsilon 3 1 and 2 times epsilon 1 2. Of course, we only showed these 6 strains, but of course again we can say that this is again same as epsilon 3 2 which is again 2 times epsilon 3 2 and so on and so forth for the other 2 components of the strain. So, what we are saying is in the contracted notations we are still talking about the stress and strain. The only difference is we are moving from these 2 subscript for stress and strain to a single subscript for stress and strain. But we need to be careful about what stresses we are talking about because especially most times we might be interested in stresses sigma 1 2 or because since we already know it is a shear stress it is in fact written in terms of tau 1 2. So, the tau 1 2 is represented with sigma 6 and similarly the corresponding engineering strains are gamma 1 2 and which is twice the tensor strain 2 times epsilon 1 2. So, this should give you a summary of contracted notations and going forward we will be using these contracted notations to look at the stress strain behaviors. So, here we summarize the stress strain relations where we have the 6 components of stress written in the contracted notation and the 6 components of strain again written in the contracted notations. These are related with the elastic constants. Again we have 6 by 6 matrix, meaning 36 independent constants. Until now we have been looking at the stress strain relations, but in common it is very common to also talk about the strain stress relations. So, meaning you want to find what are the strains, the 6 component strains in terms of the 6 components of the stresses, and we get these using the compliance matrix S, which again is the 6 by 6, meaning 36 constant. So, here C is our stiffness matrix, and S is the compliance matrix. So, if you look carefully, we see that there is of course a relation between the stiffness matrix and the compliance matrix, saying that these are inverse to each other. So, the inverse of the stiffness matrix should give you the compliance matrix, and similarly the inverse of the compliance matrix should give you the stiffness matrix. So, here before we move forward, I know that there is a slight confusion. Actually compliance start with C, but we are using X for a compliance matrix, and similarly stiffness starts with S, but we are using C. This is based on the notations people have been already using. So, we will continue with this notation for this course as well, and this is a very commonly accepted notation in most of the literatures. Next we will look at a way where we can further reduce these 36 constants to 21. For that we will be discussing about the strain energy density function, which will represent it as W. So, we define the strain energy density function in such a way that the partial derivative of this strain energy with respect to a particular strain component should give us the corresponding stress component sigma I. But we have already seen that sigma I can be written in terms of the elastic constants and the strain, which means I can replace it as C I j epsilon j. So, from this one can be integrating this, one should be able to show that the strain energy density function is half of C I j epsilon I epsilon j. So, we can do the double derivative of it, meaning dou square W by first differentiating with respect to epsilon I and then differentiating with respect to epsilon j should show us that this value will reduce it into Cij. But for the same strain energy density function, if I reverse the order of differentiation, meaning if I first differentiate with respect to epsilon j and then differentiate with respect to epsilon I, then we will end up with Cji. Since the order of the differentiation does not matter for differentiation, so this essentially means that Cij is same as Cji. So, here is the stress strain relation where we had 6 components of stress and 6 components of strain. Earlier we had this related with 6 by 6 or 36 constants, but now that we have seen this stiffness matrix is symmetric because we have shown that Cij is equal to Cji. Now we have a stiffness now we have a symmetric matrix. So, in a symmetric matrix, how many independent constants do we have? We have the diagonal and the upper matrix, the rest is symmetry. So, here in effectively we have 21 constants. Where do we get that from? So, we can start writing these as 6 plus 5 plus 4, 3, 2 and 1. This should give us 21 constants. So, what did we show? That we started with 81 constants, and because of the stress and strain symmetry, we have reduced it into 54 with stress symmetry and to 36 with strain symmetry. But now that we are assuming that this material has a strain energy density function W, then we can further reduce it to 21. That is what we have shown. Here we have shown it for a stiffness matrix, but the same arguments are also true for the compliance matrix, where there too you can write the strain energy density function in terms of the stresses. And later from this you can prove that Sij is Sji, meaning that the compliance matrix is also symmetric, and again once we say this is symmetric, we can say there are 21 independent constants. So, we have shown that both the stiffness matrix as well as the compliance matrix have symmetry, and because of this symmetry we have further reduced the number of independent constants to 21. Now, let us see what is the physical interpretation of these constants. So, for that it is best to look at the strain stress relations, where we write the strains in terms of the compliance matrix and the stress components. So, let us look at an example, a situation where let us say the only non-zero stress is sigma 1, meaning that the other stress components which are sigma 2, sigma 3, tau 2 3, tau 3 1 and tau 1 2, we are saying that all of these are 0. So, can you imagine what is this stress state? This is basically uniaxial tension. So, if you are only applying stresses or the axial stresses and the rest all stresses go to 0, now we are interested to know how this material behaves. So, what will be the value of sigma epsilon 1 or the normal strain? So, here we multiply S11 with sigma 1. And what about epsilon 2? For epsilon 2 it will be S21 times sigma 1. Similarly, sigma 3 is S31 times sigma 1. So, what does it say about these components S1, S21 and S31? So, we are saying that because of these uniaxial tension, there is strain in the direction of the loads, that is expected, that is same as what we also expect for an isotropic material. But here we are saying in addition to the strain in the axial direction, it does have strain in the transverse direction. So, in the second direction and in the third direction also there is changes in the dimensions. For an isotropic material too, we see that there is change in dimension, but we say that the changes in dimension in the direction 2 and 3 for an isotropic material are the same. But for an anisotropic material, we say the changes in dimension in the second direction is different from the changes in the direction changes in the third direction. But in addition to this, we do have the shear strains as well. So, how do we write gamma 23 as? Gamma 23 should be written as S41 times sigma 1, and similarly gamma 31 as S51 times sigma 1, and gamma 12 as S61 times sigma 1. So, bear in mind previously we said that this compliance matrix is symmetric, meaning we are trying to represent it only with the diagonal terms and the upper triangles. So, one could replace this 2 1 with saying that this is simply S12 times sigma 1 and this is S13 times sigma 1. Similarly, for the rest also we can write it in similar fashion. So, what we are just shown here is instead of using this lower triangle, we are trying to write everything in terms of the diagonal elements and the upper triangle elements for this compliance matrix, but both are the same since we know that it is a symmetric matrix. Okay. So, now let us say the same experiment is repeated for an isotropic material. So, again saying that sigma 1 is non-zero, but this is for an isotropic material. Now let us see what are the non-zero strains. So in the axial direction of the load, we expect that the strains to be non-zero, but what about the strains in the transverse direction? We know that the strains in directions 2 and 3 are non-zero, but these two strains are equal for an isotropic material, meaning epsilon 2 is equal epsilon 3 equals, both are non-zero. But what about the shear strains? Shear strains, we know that epsilon 4, epsilon 5 and epsilon 6 all go to 0, because for a isotropic material we say if the loading is simple uniaxial load, then there is no strains in any of the three perpendicular planes. So meaning that there are no shear strains, we only have normal strains for an isotropic material. But whereas for this anisotropic material where we have developed these stress strain relations, we see that it does have three components of normal strains as well as three shear strains. But now let us try to get a sense of these from this figure. So what does these terms S11, S22 and S33 signify? So for example, S11 signifies that if you are applying a load in direction 1, what is the contribution of the corresponding strain in the same direction. But if your loading is in the second direction, S22 will bring you the strain in the second direction. So which means these try to bring in the corresponding strains in the same direction of the loading. We call these as extension components. Because they are discussing about the loading direction as well as the strain we are looking at, both are the same. Now let us look at these the other three diagonal components, which are the S44, S55 and S66. What do they signify? They signify that if you are applying a shear stress, what is the shear strain in the corresponding direction. So similar to how we wrote it as extension components, these are the shear components. Meaning in the same plane, if you apply a shear stress, what is the corresponding shear strain, that is what they bring in. Now let us focus our attention into these S12, S13 and S23. What do they signify? They actually signify the Poisson effect, meaning if you are applying loads in one direction, what are the deformations in the transverse plane. So for example, if you are loading in direction 1, sigma 12, S12 and S13 will give you the strains in the other direction, these are the epsilon 2 and 3. So these are called the extension coupling. Because we are still looking into the normal stresses and normal strains. The only difference is we are looking at both are not the same direction. So if you are applying a normal stress in one particular direction, we are looking at normal strains in the other two directions, that we get from this extension coupling. So this is something we notice both with anisotropic materials as well as the isotropic materials. In both of these we do have this extension coupling. The only difference we mentioned is this coupling is same in both the other two directions for isotropic material, but for anisotropic in each direction it is different, meaning S12 and S13 are not the same, they are different. Then we move our attention to this triangle where we look at S45, S46 and S56. What do these bring in? Similar to the extension coupling, they bring in the shear coupling. What does this mean? It means that if you are applying a shear stress on one plane, there is a shear strain on the other two perpendicular planes. So, that components are brought in with this shear coupling. So, for example, let us say if you are applying tau 1 2 and we get shear strains in the other two directions, let us say gamma 2 3 and gamma 3 1. This coupling is shown by the shear coupling components which are shown in this triangle. And lastly, we have this top right square which has these 9 components starting from S14 to S36. What do these bring in? This is where you have a coupling between the normal components and the shear components. So, for example, if you have applied a normal stress sigma 1, these components will get you the shear strains. So, for example, if you apply let us say shear stress tau 2 3, this will give you, because of the applied shear stress, what is the corresponding normal strain you get, like the epsilon 1, epsilon 2 and the epsilon 3. So, we call this as the shear extension coupling. So, now after this discussion, one should appreciate that each of these terms in this compliance matrix do have a significance. So, these diagonal terms, the upper diagonal signify the extension coupling and the lower diagonal the shear coupling. So, the only difference is these diagonal terms take care of the same direction. So, if there is a normal stress in one particular direction, we are looking at in the same direction what is the normal strain. Similarly, in a particular plane, if there is a shear stress, we are looking for the same plane what is the corresponding shear strain. This is what the diagonal terms signify. But these two small triangles, the top triangle brings in the extension coupling, which we can also say as the Poisson effect. Where we are saying that if we apply a normal load in one direction, what are the corresponding shears happening in the transverse plane. And similarly, the bottom triangle we said is the shear coupling, again saying that if I apply a shear stress in one particular plane, what are the shear strains in the other two perpendicular planes. And lastly, this shear extension coupling, where we said because of applying normal stresses, what are the shear strains happening in the material. So, again to bring in these isotropic materials, do isotropic materials have this shear extension coupling? The answer is no, because simply if I take a square and I only apply these normal stresses, we see that there is no shear strains happening in this material, because it can either shrink or expand based on whether the stresses are positive or negative. So, since here I am applying stretching stresses, so the body will stretch, but it will not distort, meaning that there are no shear strains for an isotropic. But for an anisotropic material, we have this shear extension coupling, and even if you apply a simple normal strain, you will notice both the normal, if you apply a normal stress, we apply normal strain as well as shear strain. So, with this, let us summarize what we discussed in this video. So, we started with these 81 independent constants for a generalized Hooke's law taking an isotropic material, but then we said because of the stress symmetry sigma ij equals sigma ji, this got us down into 54 constants, and later the strain symmetry, again the say epsilon ij is epsilon ji, we got it down to 36. Later, once we said that if we assume that there is a strain energy density function, then we can show that the stiffness matrix is symmetric, meaning Cij equals Cj, and then we got it down into 21 constants. Though here I write only stiffness matrix, we have also shown for the compliance matrix also we showed it is symmetric. And lastly, we try to get a sense of this compliance matrix, looking at what are the different significance of each of those terms in the compliance matrix, and where there is coupling we have identified. So, with this we will conclude this video. In the next video we will look at further simplifications. We will start from these 21 independent constants, and then we will go to an isotropic material with just 2 independent constants. We will show that there are some symmetries available in the material which we can use to reduce the number of constants. See you then. Thank you.